All right, everybody.
Yeah.
Welcome to class.
Here's your homework for next week. We're going to learn about logistic regression today, and then you'll get to do it for your homework. Yes, you're so excited. Who here has heard of logistic regression?
Okay. Well, it's regression based on the logit. We will get there. And it's going to be very much like earlier homeworks. So you just find some data, fit the logistic regression to it, and then see how it does. And explain how accurate it is, things like that. All the normal stuff. And you can even use the scikit-learn logistic regression code. It's going to be super easy. You guys are going to love it.
That's okay.
Not really. No. I mean, I personally think it's going to be super easy. You guys might find it to be sarcastic.
Presumably, it's just going to be like a linear regression.
Yes, but it's different.
We don't have to know any of all the math formulas for giving us the test.
There's no test in this class.
Okay.
There's no test, it's no midterm, there's none of that. It's just project based. For your class score, your final score is 80% projects. What are the other two? You want to know? Class participation, 10%. The other 10% is your oral presentation that so many of you have been asking me about it. I just can't fit you all on the schedule. I'm going to start calling on you or telling you in class, okay, you are going to do it next time. You're going to do it next time. And we'll probably do 2 each class starting pretty soon. Okay? Because we're going to run out of time to do it. Okay, today we get to do more math. So let's start off with a math joke. A physicist, an engineer, and a mathematician were on a train in Scotland. And my family comes from Scotland, and I've been there. And the sheep are unique there. And the 3 of them look out the window of the train and they see a black sheep up on the hill. And the engineer is like, oh, look at that. Scottish sheep are black. Then the physicist says, no, my friend, you have overstated it. All you can say is that there exists one sheep in Scotland that is black. And the mathematician says, no, my friend, you have overstated it. All you can really say is that there appears to be one side of one sheep that appears to be black. The point is, mathematicians are super exact and super precise about what they say. And that's useful in theoretical math. But we don't have to be like that. We can be more like engineers. We can be a little more loosey-goosey with the math. It's got to be good enough. That's why last time I introduced the idea of the admissible heuristic. And if you use the admissible heuristic, A star is guaranteed to find the best solution. We don't really need that. We need a solution. Sometimes it gets there faster if you use a slightly non-admissible heuristic. So be a little loosey-goosey with the math, and maybe you find a good enough solution faster. So, of those of you who have already finished the homework due tonight, raise your hands if it solved it. All right. And just to do a quick survey, how many iterations did it take?
So I didn't do the single step left or right. I did it so that I could move a block to any location,
Okay.
but then that was probably
9 to 12 total computations or moves. How many total computations?
I don't have to count either, but it's 10 moves.
Okay. Okay, 40 is really low, nice.
Like 14 moves, but 4,000 computations. computations.
Yeah, it's a lot more. Any others? 10 moves, do you know how many computations? So remember how there's trade-offs with the heuristic. If it's admissible, then it's going to find the perfect answer, but it will probably take more moves. If it's not admissible, maybe fewer, but there's even a lot of diversity among just the admissible heuristics. And the ones that have more informedness are going to get you there faster. And the intuitive way to think about informedness is they're more accurate. So an admissible heuristic never overestimates. So it's underestimated all the time. And the less it underestimates, the faster you will get there, the more informed it is.
Do we print out all the states it's computing for as well, or do we just print out?
I just wanted to see, no, we, just actually, that, I see what you're asking there. I want to see the 10 first states you computed and the last 10 states you computed. Now, printing out the actual solution to the end is actually even better. I like that even better.
So if you do the solution, do we have to do the moves as well?
No. But yeah, I guess the most important thing would be nice to see those 10 moves that it found.
Yeah.
Good. Any other questions about tonight's homework? No. All right. What do you guys see when you look at this? What does it make you think of? What? Torture. Okay, medieval torture. Is it not medieval?
No, this is modern torture.
Modern torture. What kind of shape do you think it would have? Well, first of all, there's questions you don't know, right? You don't know what beta 0, beta 1 are, right? Well, I'll tell you, they're constants. They're coefficients. Drawing it in your mind? Good.
Because you're dividing by the value you're adding more to value, but the larger your beta 0 and beta 1 are and the x, the less of a slope there is, the lower that your overall value would be. So we probably start year 1 and then go down.
So
Go up.
this is
I'm
x.
being dumb.
What do you think if, let's say beta 0 is 0 and beta 1 is 1, the simplest case possible? What do you think it will look like?
An S,
An S, what kind of S? Like,
the one like on slide 2.
yes, exactly. Very good. Yes. It will look like an S, just like the one on slide 2. And you guys, I make these slides 1 or 2 days before class. You can even look at them ahead of time if you want. So it looks like that. Oh, I did it wrong. So that goes from 0 to 1, not -1. I actually drew tan H. What are some other names for this function? Nope. Weibull is very useful, but this is not that. Imagine mine looks like that. Ever heard the name sigmoid? This is a sigmoid. The sigmoid function. SIG, what is referred to up there? Now, of course, this is on some variable t instead, but basically exactly the same as if beta 0 was 0 and beta 1 was 1. You get exactly this function. Okay. There's going to be a lot of sigmoids in your life for the rest of the semester. So think about it. Get it in your head. It's going to come up again and again. But before we move on, this part of the function, the stuff that's in the exponent of e, the natural number e, 2.71878, whatever. Does this look familiar? Its format. Yes. Y equals mx plus b. This is the b, and this is the m, right? It pops up again, yet again. Okay, now, just to recap, because I was confused when I brought this up last time. This is simpler than I was making it out to be. Start at the top, you have y equals mx plus b. Then we just change the order of the x and m, because we want to make it more like the vector version. Then we create this thing called x0. Out of the blue, it's always a 1, so it never changes the b, but we put it there so that we can represent things as a vector of two things. This is a transpose set of vectors. So we get x0, x1, x0, x1, x0, x1. So since x0 is just fabricated to make the equations easier to put in the matrices, what we really had was a much simpler example where we have just x, 1. We can leave x0 out of it because it's always 1. X0, x1, and we have y. And this first one, x1 is -1, that's -2. -1, -2. So that one. Then 1 and 0. And then 2 and 1. No, 2 and 3. So if we have those 3 points, this W0 and W1 would be the perfect line through them that minimizes the squared errors. Which one of these is our M and which one is B? You can trace it back to the top if you want.
W0 is B.
Yes, that's right. W0 is what gets multiplied by this, 1 thing, right? And M gets multiplied by the x1 value, mx1, really. So this is what it looks like in vector form. And you can imagine if you add another variable instead of x1, let's say you have x2 coming out of the board here. The two of them will then work together to find a single y value. If we could envision yet another dimension, we'd have, x3 going in another dimension, contributing to that same y value. And this would simply get wider. And here, this would get longer. You have W0, W1, W2, W3, and eventually W1000. These are very general tools that can apply to everything. Then we take this, y equals x1 W1, x0 W0. And we can turn that into y equals x W. This is the y. This is the x matrix. And this is the W vector. And this, once we have in this format, it looks so easy. It's an equation with just 3 terms. That seems pretty easy, doesn't it? It might be 1,000 variables. It might be 10,000 points. It doesn't matter at that. Now, from here, we have that choice. We want to figure out what the W is. We can do it one of 2 ways. Who remembers what the 2 ways are?
Is it one gradient descent?
Yep.
And the other one is you do the full transpose.
Yes.
a mess.
Yes. I mean, it doesn't look that ugly. I mean, it's just two more steps, right? But as I think you're the one who said, computing this inverse could be n cubed. Be very computationally intensive, and that's the case when you want to use gradient descent. Now, what's nice about this is that if you do it, you know you have the exact right answer. Gradient descent will get you really, really close to the right answer. Okay, any questions about that? All right, there was a question last time about the difference between A star and Dijkstra's algorithm. If you click on this link, you'll get to this website, which shows a play, it can play back for you how Dijkstra's algorithm actually works. And the main difference is that, let's say you put in a starting point, and I chose vertex 3 right up there as my starting point. Dijkstra's algorithm will compute the most efficient path from 3 to every other node, not just the goal node. That's one of the main differences here. So if you need to know how to get everywhere, this is what you should do. But if you need just to get to your goal, this is not your best choice. All right. What if our data does not look like this? For instance, let's say you have a bunch of inputs on the X, but your Y are not, this nice smooth thing. Let's say the Y is binary. Let's say the Y is, yes, this tumor is malignant, or this tumor is benign. Just binary data. Is it easy to fit a line to that? No. You could do it, but it'd be weird, right? So if we have binary data, true or false, let's say that these are all the falses, those are all the trues up there. 0 false, 1 for true, whatever it is. Obviously you can flip it, no big deal. If you were to draw a line, just do normal linear regression, you get something like this, right? And that'd be the best you could do. It wouldn't be a great model for predicting how things work though, right? The whole idea of a model is so that you can guess what unseen data will be classified as before you actually run a test. So let's see what we can do. Our old hypothesis was that line, y equals mx plus b. Whenever you see things like h subscore theta, that's hypothesis. Remember that there's a lot in the literature, there's a lot of ways to refer to the same things. So y equals mx plus b, or equals x1 w1 plus w0 x0, or theta 1 x1 plus theta 0 x0, or these are there's many ways to refer to the same thing. And depending on which website or book you're looking at, it's going to choose one or the other. Sometimes the variable is t instead of x. This would be a vector matrix formulation of the same thing. Okay, so our old hypothesis was just that line. Our new hypothesis is going to be the sigmoid. And we're going to alter its shape, contort it a little bit to fit our data. What is the range of it going to be?
0.
Always? Will that ever change? No. It's always 0 to 1. And the original equation we looked at, no matter what beta 0 and beta 1 you put, the range is always 0 to 1. How do you think beta 0 changes it?
It shifts it horizontally.
Shifts it which way? Horizontally? Yes. Very good. Okay, here's another really fun link for you guys. Wolfram Alpha. Okay, so this up here is, of course, 1 over e to the negative, and I put plenty of parentheses to make sure it does what I want it to do. I have a beta 0 of -1 and a beta 1 of 1. And I'm plotting it from -10 to 10. It goes from 0 to 1 on the vertical. What other values should we try? How about you? What should I try for beta 0 and beta 1?
5.
5 for beta 0 and beta 1?
5 is here. We'll go 10.
10. Oh, wow, very sharp. So which variable does the sharpness come from? The 10, yes. So let's see that by bringing the 10 back down to 1. Yeah, very smooth now. And how much was it shifted? By 5, but -5. That's one thing to keep in mind. It shifts the opposite way. So what if we put in like actually 2 more values? You
37.
37. 4. All right, wow. It has trouble because it's only applying from -10 to 10. So if we go -100 to 10, then we can see it. All right. Now, if we go something like 0.1, we'll change this to like a -2. Is this going to be smoother or sharper? Very good. So smooth, we actually have to expand the area we're looking at. And I shifted by -2, so it's, oh, it's expanded even more. There. So yeah, very smooth. Okay. Now we know what beta 0 and beta 1 can do. So I'm going to add a new concept. We're going to think about this as a probability. Remember, the highest it can be is 1, right? And we're dealing with things that are either 0, false, or 1 true. So think about the distance from 0 up to the function, then from the function up to 1. So right here, where it intersects with 0.2, what does 0.2 represent? Is it the probability of being true or false? Probability of being true. And its probability of being false is therefore yes. See, math is easy. This is what it looks like when you start to fit your sigmoid or logit function to your data. Let's say we're talking about this point right here. Our function tells us that it is, 0.18 likely of being true. And it's actually a false one. So that's good. We would have gotten that one. Which one would we get wrong?
On our type 2.
This one right here? Yeah. We would totally get this wrong. What does our model, our hypothesis, tell us the probability of this one is?
0.85.
Yeah. So we're going to get that one wrong. This is not perfect, and they never will be perfect. There's always outliers in almost everything you study. There will be outliers. What is something we can do to make this more accurate?
Make a threshold.
Well, threshold is naturally 0.5, but you could change that if you want. So everything above 0.5, we say we're going to hypothesize that it's true. And if it's below there, we're going to hypothesize that it's false. So if we do that, we'll get a certain number of them right, a certain number wrong. Is there anything we can do to that curve to be more accurate?
Make it really steep.
Yes, make it steeper. So we're going to make it steep. But first, let's talk about this root function that you don't really have to understand, but you should be aware of it. It's kind of a general way to describe a function. Likelihood. Argmax just means choose the maximum value that this function can give you, or this set can give you. This just says get the likelihood of, remember what this is? Someone tell me what theta represents, the capital theta of that. Yes. What values might be in that? No. Yes. Beta 1, beta 0, or W1, W0, or theta 1, theta 0. Maybe there's a theta 2, theta 3, theta 4. But the capital theta that you see there just represents all those values that you're using in the bottom of that logistic function, the sigma. And of course, y is what you're going to max out. You want the, but that's the, the output. But this is called the maximum likelihood function, and it's kind of an idea. It's like a meta idea. What do you think maximum likelihood would be computed from here? How would you compute the likelihood? Not the maximum likelihood, just the likelihood of this curve. It's almost like what we did before with squared errors. You guys can totally get this. Think about if it's worse, like
You know, he said sharper would make it better, but if it's smoother, it would be worse.
So it's just the distance of like the point of the line. that you put it.
Yes. And if you want, you could square them. Or if you want, you can just add them up. L1 or L2 norm, L2, L1. But that is what you're going for. You want to minimize that distance. But you don't go the same direction for all the points, do you? From the blues, you start at the top and go down. From the red, you start from the bottom and go up. Okay, hypothesis. This is the way you might write your new hypothesis. Instead of mx plus b, or instead of theta x, it's actually transpose here. Instead of just theta transpose x, now we got to put it underneath this in the denominator in a exponent of e. And when we do this, we get that nice curve. And now we know how to change the curve. Theta contains, you know, another way to write this would be beta 1 x1 plus beta 0 x0. It's all the same equation. So inside the theta, we change it to be whatever we want to minimize those errors. And we write it like this. So you can think about it as a cost, right? Now, what they like to do is they like to take the log of your hypothesis. Now, it's either the value of the hypothesis minus 0 or 1 minus the hypothesis. So if y is false, you're doing this. Or if y is 1, you're doing this. Now, the reason why we choose a log, it just makes the math nicer. If you want to deep dive on that, go to this last slide and you can click on the YouTube video here. That will go into this idea of log odds and why it's a good idea, but we don't need to do that now. Just remember that we're dealing with two situations. We got for the trues, we compute that cost. That's the error, we compute it one way. And for the falses, we compute it another way. That makes it a little bit uncomfortable, right? Because we don't have this one equation that always works. We've got two equations, so we have to always be aware which kind of point we're dealing with. Well, there's a trick around that too. So y is always 0 or 1. There's no other choice. So we can do this. We have one cost that's always this equation. This is perfectly consistent with that two equation setup we saw before. Why?
Because y is 0 in the first term, that's why y is 1.
Exactly. So we get this nice elegant thing where it's one equation. You can just use this all the time. Of course, the code already has this in it. But we're going through all this so you guys understand the mechanics. So that first part is used if y equals true, and the second part if y equals false. But you can just have the same thing in there all the time. Now back to this, I wanted to make the point, which someone else already recognized, we have that b and mx in there. Same equation coming up again and again. Okay, now I want you to start to consider the case of when we have an x1 and an x2. Logistic regression on two independent variables with
would look like this. See how the red points are still the false ones and the blue ones are true. The error is computed exactly the way as before, right? You will take the distance from that point down, or the distance from a false point up to that surface. Now your actual cost function is going to use the log of that. But same idea. And you can see the same concept here, where if you made it sharper, then you would become more accurate, right? Everybody see that? Okay. Scientists realized there was something wrong with making it sharper. And the way they resolve it is by adding something extra to the cost. Think about kind of like taxes. The government taxes things they don't want you to do too much of, and they don't tax the things, so they give you a benefit for the things they want you to do more of. At least that's the theory. So if we want the model to act in a certain way, we can tax it, give it an extra cost when it does the things we don't want it to do. Now, if you look back at this, try to imagine if you made it sharper and sharper, there'd be a point where everything here except for one would be classified correctly. And everything above, except for maybe that first point, would be classified correctly. Why would that ever be bad?
If I've overfit the data and you're trying to generalize it.
That's the word. That's the word of the day right there. Overfit. And if it overfit, then it doesn't. What's that word? It starts with G that you said?
Generalized.
Generalized. If it overfits, then it doesn't generalize. And you want it to generalize, otherwise there's no point in having a model, right? If it doesn't work except in your training set, then it's kind of useless. So we need to give it a cost so it won't do that. And to show you what it looks like in 2 dimensions, it's actually a little clearer. So let's pretend that we had, oh, this is what I was talking about before. This is more accurate than this, but maybe it's overfitting. Now, in the 2-dimensional case, you can get really convoluted. Now, there are some people who, instead of having beta 0 and beta 1, they'll have also beta 2 and beta 3, and maybe they're not other variables. Some people okay. So some people would have something like okay, so some people make this function very complex, and then they throw in an x1 squared and an x2 squared, maybe an x3, and then x3 squared, and x3 cubed. You can get as complicated as you want, but in just 2 dimensions, x1 and x2, you can add squared terms, and you can get things that get very, very accurate. So let's say you have X1 and you have X2. You've got some trues and some falses. Your curve can be, in those two dimensions, can become so convoluted and weird, it's no longer just a smooth sigmoid because you've added these square terms, which you won't do for your homework. But if you did, you could get some weird thing like this, that in these areas, the curve pops up above the threshold. Below those areas, like here, you can think of it as a hill, okay? It's a contour map for a hill. And down here, that's a valley, and that's a valley. These are valleys. So in the valley, it gets all of the false ones correct and all of the true ones correct. That does not generalize.
Would forward or backward selection help in not linear arrays?
What do you mean by forward backward?
If you have, let's say, multiple variables, you can use the level of like effect each one has. If it's above a certain threshold, you put it in. If it's below a certain threshold, you take it out.
So you have many variables and you're choosing the best ones from them.
Yeah.
That is a good strategy. And some people do these tests where they start off with all the variables, remove one, see if it improves or how much it doesn't improve, remove another one. They do all these different tests to figure out the best set of variables. And there's some more efficient ways to do it too. But let's pretend we only have two variables and they're these, X1 and X2. If you get a curve like this, I mean, obviously you can make it simpler by just getting rid of the squared terms. But another way, if you wanted to keep the square terms in there, we want to put pressure on making that curve smoother, right? And in the same way, you see it here in 2 dimensions. If it gets smoother, it would look more like that purple line. See that? How do we pressure it? How do we give it a tax to make it do that? And in 2 dimensions, it would mean going from here to here. Just looking back at the costs, what do we add to it to make it want to be smooth? Remember where we started. Beta is really these betas, right? What is the smoothest value for those betas? Small, yeah, but well, 0, I guess it'd be smooth. It'd be infinite, it'd be a straight line. But yes, smaller makes it smoother. Is there, when you're trying to make it smooth, is there any pressure on beta 0? No pressure at all. So you really don't care about beta 0. But beta 1 is the one you care about. And if you need them, beta 2 and beta 3. So if we want to put pressure on it to make it want to make them small, we just need to include them in there. So remember the betas, W's, same thing. On the Wikipedia page site, it uses W's, at least that one. Other ones I think uses theta. What do you think this lambda would be? No, it's just a number. You said it. The regularization parameter is what they call it. What I don't know is why you have to divide it by 2. Why not just set it smaller, you know? I don't remember that part. So if you have, beta 1, beta 2, beta 3, That's 3, m equals 3. So you're going from 1 to 3. So you would want all of them to be added at the end. So you have your normal costs. And you're gonna straight up add to it lambda over 2 times beta 1 plus beta 2. If these get big, that increases the cost, right? So you want to put a little pressure on this model to not make them big. It's going to want them to be small. Now, there's no perfect answer. Depending on how generalized versus overfit you want to be, you will set that lambda parameter differently. Now, it's not called lambda in the code. So when you use, if you use the scikit-learn logistic regression package, this C value, which defaults to 1, is that lambda. And you can increase it or lower it to make the tax, the regularization parameter, higher or lower. Makes perfect sense, right? We all love math a little more now, right? All right. So, starting in a couple weeks, well, not the homework you're doing now, but the homework after that, we're going to start getting into NIM players. So to get in the mood, I need a couple volunteers. People who don't get farmers. Santiago, how about you? And how about you? Come on up. And others will get chances to play a game of NIM. You know. One, 3, 5, 7. You're missing one from the third row. No, you were playing that one. You don't have to record, that's fine. We just want to see who wins. You made 2 out of 3. You have to take
Some amount from what you know.
All right, good job. 2 more. Unless you win this one too. Then. They take turns, who goes first? Is that a fully erased one on the right there?
Yeah.
Oh, okay. We're at a tie now. Tiebreaker. All right, and we're gonna pause. Okay, 2 more volunteers. Volunteers, or else I'll choose you guys. Come on, who wants to play? It's these games, it's fun. Yeah. What's that? Or jump in, okay. Hey, Chef, once again. Who went first that game? You had the advantage then.
I know. That's the.
All right. 2 more.
How about you?
No, I still got it.
Why not?
Not this case. You read that. I think it's.
Yeah,
no,
I just switched back over.
Good job. 1 more, yeah, best out of 3. All right, we're tied up, right?
No, she won one.
Oh, you won twice, all right. Good job. All right, who's next? Come on, guys, get excited. All right, I will choose again. How about two of you? One. You made the best moves you could. All right. Good job, guys. Okay. One more pairing. This will be the last. Volunteers, guys. Any volunteers? All right. Anyone else? No? Okay, we'll play. And I'm not using any special strategies. I'm just gonna play with my gut. No, I'll probably might lose. I'm not gonna play with the nim sum thing. There is that calculation you can use, which maybe Santiago is doing. Who knows? I'm just play with my gut. You go first. My God. All right, this is okay. Cheater. Yeah,
Honestly,
if my plays were consistent 100% with engine online, then I guess you don't need it. Okay, I go first this time? Did you go first last time? I don't either. Go ahead. Good job. All right. One more game. Boy, 2 out of 3.
No cheating.
No cheating this time. Hey, this is over the board.
I don't think the engine gave you the right way.
And none of us have those radio frequency beats. Okay, I go.
Incredible one.
All right. Yeah. All right. Thank you, everybody. Any last questions? Math is fun, isn't it? Oh.